Yep.
Okay.
Thank you very much. Okay, I'm going to tell you about comonads on set. You may have heard that space is dual to algebra, right? Aren't we always hearing this? People like to say this for some reason, that there's this duality between space and algebra. You may have also heard that monads describe algebra. Specifically, monads on set are basically the same as algebraic theories. But have you heard that comonads on set are spaces? This talk is about that. Comonads on set as a generalized kind of space is what this talk is about. Okay, so if I'm claiming that comonads on set generalize spaces, then they should at least generalize spaces. And this is true. Every topological space is identified with a certain comonad on set. And here's one way to see this.
Wait.
For any space, there's a forgetful functor from its category of sheaves to set, sending a sheaf to the sum of its stalks. And this functor is comonadic. And the topological space can be recovered from the comonad. But does this justify thinking of all comonads on set as generalized spaces? And probably you don't think so. So let's see if I can defeat you in this talk. So the plan for the next 15 minutes is I'm going to try to rebuild point set topology from the ground up with some kind of categorical attitude. And we want to keep all the basic concepts of topology. So we want to have points and neighborhoods and continuous maps and bases and all that stuff. But instead of founding all of these topological ideas on subset inclusions, we'll found everything on maps between sets. So it's a more categorical kind of doing it. Okay, so that's the plan, to build a definition of space from first principles. And then the magic trick is going to be that when we do this, we end up with a comonad on set. Okay, so that's what's going to happen if everything goes as planned. Um, if we want to rebuild spaces from categorical principles, maybe it's a good idea to focus on continuous maps of spaces. So, what is continuity saying? It's supposed to capture that infinitesimal neighborhoods are sent to infinitesimal neighborhoods. This is supposed to be what continuity is capturing. But what is an infinitesimal neighborhood? And the main guiding idea for us today is going to be that an infinitesimal neighborhood is a formal limit of sets, and everything will pretty much fall out of this. Okay, and an infinitesimal neighborhood in a space is a formal limit of sets. So let me try to convince you this is reasonable. Here's what formal limit of sets means. A formal limit is usually an object of the free completion of a category. Technically speaking, you would just restrict to the small functors here if you want to talk about small formal limits of sets, small functors in this functor category. There are some large formal limits of sets in this category, but to keep things simple, let's just say a formal limit of sets is an object of this category. And here's how this idea works for topological spaces, familiar topological spaces. We're going to call the formal limit of all neighborhoods of a point its halo. On this slide, it's written what that means explicitly. The halo of a point is a certain formal limit of sets, an object in this category, the formal limit of its neighborhoods. This is how you take a formal limit. Okay. Feel free to stop me if you have any questions also. Um, so here's the justification for this definition of halo. A function between topological spaces is continuous just if it induces maps of halos. And this is really just a way of rephrasing the epsilon delta definition of continuity. Mapping into a formal limit means mapping compatibly into every set in the diagram, but mapping from a formal limit into a set just requires mapping out of some set in the diagram. This is how formal limits work. This is sort of the concept of a formal limit. So formal limits really do capture the idea of infinitesimal neighborhoods. Um, so yeah, let me know if you have any questions about any of this stuff. So I'm saying that the way that formal limits work is recovering the epsilon delta definition of continuity. Okay. And moreover, it's possible to recover the topological space as a certain structure defined on its halos. Um, the data of the family of halos is itself a formal limit of sets, which we can write as a formal product of formal connected limits. Here, this X is the set of points in our space, and each point has an associated halo, an associated formal connected limit of sets. Okay. And to recover the structure of a space, we also require a distinguished point in every halo, namely the point itself. And this is given by a map from the point to the formal limit X, or equivalently, a map from the point to each halo. This is picking out the point in every infinitesimal neighborhood, the point itself. And the last piece of structure we need is from the system of neighborhoods axiomatization of topological spaces. We have to specify how these halos cohere as a space. And the principle is that neighbors of neighbors should be neighbors. So here, this description is taken from the usual axiomatization of topological spaces in terms of neighborhood systems, but we've replaced subset inclusions with maps of sets. And this thing may look pretty complicated and possibly unmotivated, but all this is captured by a map of formal limits of sets from the composition of endofunctors xx to x. And if you unwrap all the details, you get a rigorous version of what was on the previous slide. So here's what a space is in terms of these infinitesimal neighborhoods, in terms of these formal limits, in terms of these halos. You have a formal limit, that's the family of halos, and you have this unit map picking out a point in every halo, and you have this multiplication map saying how the halos go here, saying neighbors of neighbors are neighbors. And then you need some compatibility conditions that ensure everything glues together well. And what this is it's a monoid in formal limits of sets. So a space, the way I'm defining it today, is a monoid in formal limits of sets. And that's equivalently a monoid in the opposite of endofunctors on set, and that's a comonoid in endofunctors on set, and that's a comonad on set. So spaces, generalized spaces in this way, are comonads on set. Now, there are other monoids in formal limits of sets besides topological spaces. For instance, monoids. Composition behaves as Cartesian product on the representable functors set to set. So comonads carried by representable functors are exactly monoids in set. They are the monoids in formal limits of sets where the relevant formal limit is just a set. And more generally, a small category is a polynomial comonad, or equivalently, a monoid in formal products of sets. And in these generalized spaces, the neighborhoods can feature multiple instances of the same point, modeling multiple ways of containment. So these are, we think of arrows between objects as a kind of nearness in this space. So comonads on set strictly generalize both topological spaces and categories. But more generally still, inads or toposes equipped with enough points are examples of comonads on set. Inads were introduced by Richard Garner in this great paper, Inads. Inads are to toposes as topological spaces are to locales. So they're a way of putting points back in toposes. And much of the content in this talk is inspired by this great paper, Inads. But comonads on set are still more general, and the topological language still works for talking about them. All these concepts from topology generalize to talking about arbitrary comonads on set. So you can talk about bases of comonads, and you can talk about points, and you can talk about neighborhoods, and you can talk about these infinitesimal neighborhoods, these halos, and you can talk about sheaves. That's maybe the most important thing on this slide. The coalgebras for a comonad on set are the analog of a sheaf of a space. And when you specialize to the comonads corresponding to categories, you get C sets, you get functors into set from the category, which is a co-presheaf. So everything works out nicely. Let me talk a little bit more about bases. The comonad on set corresponding to a topological space is also easy to construct from the data of a basis of that space. So let B be a basis of a topological space, and we'll also denote by B the poset of basic open sets and inclusions. And then we take the density comonad of the forgetful functor from this poset into set. I'm not going to go into the details of density comonads, but they're a very natural, well-known way of constructing comonads, codensity monads and density comonads. You can look them up. And this very simple construction gives us a topological space, gives us the comonad corresponding to a topological space just from a basis. And in this precise sense, comonads on set are an analog of topological spaces where we replace inclusions of subsets with general maps of sets. So instead of a basis consisting of subset inclusions, you could take any functor into set with that's well behaved enough so that it has a density comonad, and you can get a comonad, that's the density comonad. So here's an example. If you take the category of all sets and surjections to be your basis, this has a density comonad, and it's an interesting comonad. Um, Usually the basis of a topological space is a diagram of subset inclusions, but here we have a space whose basis consists of surjections, and you get this interesting situation where neighborhoods that are closer to a point actually have more elements. Um, so this is kind of a interesting concept to think about, but the coalgebras of this thing are also natural and nice. They're partition sets. Um, Here's another example of a basis for a comonad. This one's going to be an inad. Um, so this is a basis for a category-like structure with one point. So it's kind of like a monoid, and it's similar to the monoid of reals, but only an infinitesimal neighborhood of zero is defined. And this serves a role in continuous matters analogous to the monoid of integers in discrete matters. So this is I think, a very natural example of an inad, and we'll use it again in a minute. Now, I've been sweeping something under the rug throughout this talk. If comonads on set generalize topological spaces and categories, then what are the comonad morphisms? Surely these should be continuous maps and functors, but they are not. In terms of formal limits of sets, what they do is they map forward on points, but backward on halos. So this is not a continuous map if you just take the usual definition of comonad morphism from category theory. You don't get continuous maps. Still, it's an interesting and useful kind of map on categories. It's a retrofunctor. This is a well-studied concept. For example, retrofunctors into the integers from a category give a kind of discrete vector field on the category. And similarly, a comonad morphism from a topological space into the continuous analog of the integers mentioned earlier gives some notion of a local flow on a space. So this kind of map that goes forwards on points and backwards on halos, while it's not continuous maps, it's still interesting and possibly useful. But where are the continuous maps hiding? We can actually fix this problem with a different definition of map between comonads on set. And I'm not going to go into the details, but it does recover functors and continuous maps for categories and topological spaces. And it's the same definition as Richard Gardner used in his paper on inads. You can adapt that to general comonads on set. It may not be clear immediately how to do that, but it is possible to do. And not only this, the two kinds of morphisms of comonads on set assemble naturally into a double category of comonads on set. And the two kinds of morphisms of comonads on set, when you these give functors and retrofunctors when you specialize to categories, and the two cells between functors in this case are natural transformations, as we would expect. And the two cells between continuous maps between topological spaces turn out to be pointwise specializations. So I think this is a nice natural thing. We get this double category of categories and functors and retrofunctors as a special case. And I don't know, maybe people here already have seen this, but as far as I know, the known double category of functors and retrofunctors is flat, which means that there's at most one two cell of every boundary type, but this is a double category that's not flat. So it's interesting. If anybody has seen this before, please let me know. And that's the end of my talk, but I'm hoping to have a paper up on this stuff soon with Kevin Carlson and David Spivak. So stay tuned for that. Um, yeah, thanks for coming.
Yeah, let's thank Aaron for a great talk. And are there questions or comments? Actually, I have one. Well, and Simon is next. I just want to quickly ask, do you see a relationship between the double category, the flat double category that we know about and the one that you get?
Yeah, so there's a functor from the flat one into this one.
Ah,
Um, so yeah, so the way you get this double category is you can look at continuous maps and comonad morphisms as uh, lax and colax comonad morphisms between slices of set of the form delta of the form of a reindexing between a slice. And this kind of thing, when you have lax and colax um, comonad functors in a two category, in general, you'll get actually two different double categories. Um, and one of them in this case is the flat one, and the other one is the non-flat one, and you'll get a functor between them. Yeah,
nice. Okay, thank you. I look forward to the paper.
thanks.
Simon, your question.
Yeah, can you hear me?
Yes, I can
Yeah,
hear you.
yeah. So thank you very much. That was super interesting. I was already familiar with the idea that fiber product preserving comonad were spaces.
Okay.
And could you give me some intuition of what the non-fiber product preserving one correspond to? Or rather, if I think of a comonad, general comonad as a space, what does it mean that the comonad is fiber product preserving or is a ionad compared to the more general cases? Like what kind of property does that correspond to?
Sure, yeah. So right, so the fiber product preserving ones, those are the inads, right?
Yeah.
Um, yes, and there are more general ones. So for example, the density conad of those surjections that I had earlier, that's not an inad. Also, you can do some construction where you take a category and then you basically quotient the comonad by some symmetries of the category, and then you'll get a comonad, and that usually isn't going to be an inad. So, for
Mhm.
example, you could take the indexing category for graphs with two objects and two parallel morphisms between them, and you could take the automorphism that switches those morphisms and
Mhm.
quotient by that, quotient the comonad, and you will get something whose coalgebras are undirected uh, multigraphs, which is it's like forgetting the distinction between source and target. And this thing is also not an inad, so um, yes, it's I guess it's hard to intuitively say what the exact distinction between inads and non-inads
Mm.
is, but yeah, you can some with these more general ones you can capture some kind of behavior like forgetting order of
I
morphisms.
see, I
And
see.
you can forget multiplicity of morphisms as well with this surjection thing. So it's something about forgetting order, I think.
Okay, thank you.
Uh,
Bryce, you're next.
Hi, Aaron. Thanks for the interesting talk. I guess I should say I have seen this non-flat double category of functors and retrofunctors before.
Okay,
So maybe we can
great. Great. Yeah, I would
talk
love to
about
talk
this.
more about that. Yeah.
Yeah. I had a couple of questions otherwise. So wondering if you looked at, say, co-modules between your comonads as part of
Yeah.
more.
Uh-huh. Yeah, we've looked at that. Um, yeah, so the comodules between polynomial comonads are these parametric right adjoint functors between three sheaf categories.
Yeah.
And in this case, we weren't able to get something quite as nice as that, as to say like a comodule between our arbitrary comodule between comonads is just a functor between coalgebra categories. Like that's maybe the ideal thing that you could hope for, but that doesn't seem to be true. But what does seem like it might be true is that a if you have a bicomodule where the carrier of the bicomodule has some limit preservation properties, satisfies some mild limit preservation properties, then it'll probably, I think it's going to correspond to a functor between the coalgebra categories that also preserves that kind of limit. But you need to at least preserve um, co-reflexive equalizers. There's this
Mhm.
weird stuff that comes up about co-reflexive equalizers where all comonads on set automatically preserve co-reflexive equalizers. And that makes a lot of things easier in the theory, but not all functors on set are just automatically going to do that. And that makes some things about thinking about bicomodules harder for some reason, but I don't completely understand that.
I see. Thanks. And maybe my second question is, I was wondering how important set is to this story.
Mm-hmm.
I mean, we know, like for polynomial comonads, we can do this on locally Cartesian closed categories, for instance. Like, do you need to be much closer to a topos, or do you really just need set for this story to work? Or
It seems like some of the Boolean properties, like actually the Boolean topos, it being a Boolean topos is somehow important, because when you're doing a lot of the constructions, you want all comonads to preserve co-reflexive equalizers. Um, you use this when you're kind of lifting comonads to slices and things. Um, so as far as I can tell, it seems like you need to use Boolean properties of set to get that. But I'd be interested to see what else generalizes, because I think you could probably do a lot of it in the general context, but I don't know. Yeah, thanks for the question.
okay, thank you.
Let's thank Aaron again.